Welcome to my video on the GoApe Oral Piano Tuning System Piano Tuning Myth number 12. Many people say that electronic tuning devices produce a better tuning than the ear does. Let's explore this. How does an electronic tuning device know when is the best pitch for a piano string reached? Well, let's look at an ideal tuning. You see here we have A4 equaling 440 Hertz. And each octave is either doubled or halved to produce the ideal tuning. We can see this when we look at the ideal octaves. So an ideal A440 would have its second partial at 880, third partial 1320, fourth partial 1760, simply multiplying the fundamental frequency by the partial number. Now let's look at A3, an octave below. We have half of 440 being the fundamental, and then the second partial is 440, third 660, fourth 880, and you can see that the second partial of A3 and the first partial of A4 line up perfectly. Similarly, fourth partial A3, second partial A4 line up perfectly. Let's look at A5. We double 440 to get 880 and add all the partial frequencies above that. And if we increase the partial frequencies above A4, we find out that a lot of these partial frequencies match. And in fact, at every coincidental partial, they are exactly the same. In fact, with A3 as well, and even between A3 and A4, multiple pure octaves at every partial. That's an ideal octave. What about an actual octave? Well, we start with A4, the fundamental 440. But the second partial is not, it's higher. That's because of inharmonicity. So in this case, let's say it's 881. And then instead of 1320, 1324. Instead of 1760, 1766. These are not the actual numbers, they're just demonstration. Every piano has a different inharmonicity. And remember, we're talking about an electronic tuning device, and in order to describe how accurate these devices are, we need to know what they have to do. And what we're doing is we're describing an ideal tuning, and then we're going to describe the actual tuning that must be on the piano to make it sound good. We're starting with the ideal octaves, now the actual octaves. These are the frequencies that are sharper than predicted by the simple formula of partial frequency times fundamental. They don't line up. So what can we do? Well, we can start changing A3, bringing it down, lowering it, so that we can get a situation where we have these 4-2, 6-3 partials almost lining up. So we have this narrow 6-3 here and a wide 4-2 here. And if you don't understand 6-3 and 4-2, you can look on my site for a description of that. It's the octave sizes and check notes video. But it's conventionally accepted that the best octave size for a real piano with inharmonicity is a wide 4-2 and a narrow 6-3. So this is what we're looking at as the best sounding octave. But look, A3 now is less than 220, which was the ideal pitch. So we say now that A3, A4 is stretched. It's a stretched octave because it's wider than double. Let's look at A4, A5. Well, if we're going to line up A5 with the second partial, which is 881, we already have a sharp A5, sharp from the ideal. But when we start looking at these higher frequencies, we see that we have to raise A5 even more to 883, for example, so that we get the wide 4-2 narrow 6-3. So with these frequencies that are now actual octaves that sound good, we see that it's not 220, 440, 880. And we're going to take these notes now that we imagine are better sounding in this imaginary piano. Put that onto the ideal tuning curve. This ideal tuning curve, as we talked about, has doubled and halved the 440. So we have the 220 and the 880. But in this case, when we use actual octaves, we find that the A3 is a little bit flatter than what would be ideally predicted, and the A5 is a little sharper. The green line here represents the ideal tuning. But if we're going to talk about an actual piano, we see that the green line is changed so that A3 is flat from ideal and A5 is sharp from ideal. And similarly, we can do this over the whole piano. And a man named Railsback did this years ago, recorded and measured an actual piano that had been tuned and found this. So we call this the Railsback Curve. Now this particular curve is different for every piano. And the amount that it changes from the ideal we call stretch. But we have a grand piano, doesn't have much stretch, then a typical upright, and then the spinet, the short strings, have a lot of stretch needed in order for the octaves to sound good. So the question is, how does an electronic tuning device know what stretch to put on a piano? Well, the first thing you have to do is you have to sample some notes. Different ETDs use different ways of sampling notes. Some require 4 notes, some require, I think, 3, some require 6, and some measure every single note. So once you measure the notes, then the ETD will estimate the inharmonicity of each string and then will create a stretch curve based on the notes that were measured. And you can see already that this stretch curve is not matching all of the inharmonicities of the sample notes. So what's the problem? First of all, let's say, well, what's the goal? Why are we even doing this? We're trying to make equal temperament. And what is equal temperament? Well, progressively beating intervals. So major thirds beat slightly faster as we go up chromatically the scale. Perfect fourths as well, but they're all uniformly wide. That's basically one criteria for equal temperament. It's a pretty good one. Let's look at what the ETD does. First, you measure the sample notes. Well, in the process, the ETD measures the frequencies of each partial, but the problem is that these strings don't have a constant frequency, although the ETD is going to use one number in its calculations, but the frequency of each string and its partials are not one number. They're fluctuating. But the ETD will just approximate one number. And then after it gets that frequency, it's going to fit a mathematical curve to all the partial frequencies. In other words, it will measure each partial frequency, and then it will create a mathematical curve that fits as close as possible all those partial frequencies. And that is the inharmonicity of that string. Then it will change the frequency of each string so that the inharmonicity coefficient will fit onto this approximated line. So here are the approximations that this ETD is making. First, it's approximating the moving partial frequencies. Then it's approximating a mathematical curve to predict all partial frequencies of each string, even those not sampled. And then it will fit a stretch curve so all the partials fit some preconceived criteria. Once the curve is approximated, now it has to take each of those inharmonicity coefficients and back calculate from those partial frequencies what the fundamental frequency should be. And now you're going to have the ETD tell you when you have set a fluctuating pitch to the static pitch that the ETD thinks is accurate. One other thing. When you're using an ETD, you only really have to measure one string at a time. Usually you start at the bass and go through to the treble, setting each string once as you go. Good technicians, if they're using an ETD, will do it 3 or 4 times because the strings drift. They don't stay where you put them. But the Go Ape open unison technique allows you to listen to a string's pitch multiple times and know if it's drifted and correct the drift. So that's 6 levels of approximations, all creating some error at each step. And the goal is to make progressively increasing interval beat speeds. Well, how do we tune a piano by ear? We set progressive interval beat speeds and uniformly wide perfect fourths. Hold on a second. Isn't that the final goal of the ETD after 6 steps that contained errors? Yes. When we tune by ear, we're making 1 step to get to the final goal, whereas the ETD has 6 steps of approximations all the way. Also, the fluctuating frequencies are averaged out because we're listening to beat speeds. Not the frequency of the note, but the beat speeds. So if a beat is 1 beat per second, there's a lot of frequencies in there speeding up and slowing down, but after 1 second, the beat has averaged out those frequencies. And when we use open unisons, we eliminate Weinrich error. ETDs do not even allow you to tune 3 strings at once. You tune a single string, then you add the other unison strings, and that's when drift can happen, up or down, and that's Weinrich drift. With tuning by ear, the only error is that you're setting beat speeds increasing by 6%, which is equal temperament, but you can only hear down to 3%. So there is a little bit of error there. But with the Go Ape technique, we can make that even smaller by listening to other criteria. So why do people think that electronic tuning devices are better than the ear? Well, it takes a lot of time to train the ear so that you can hear beats clearly. And that is what you need to do if you want to tune a piano by ear. You need to be able to hear those beats clearly. It's simple as that. There's nothing more difficult. But too many technicians think it takes too much time to learn. It takes about at least 2 years before your ear is really on. And some think they'll never be able to hear beats well enough to tune as well as an electronic tuning device. So in the process, they give up because the machine is there. And they go and they use the machine under the false assumption that computers are more accurate, but really because the computer is better than they are at the moment. But if they just kept at it, they would be better than the computer. And the reason why people think the computer is so good is because they make qualitative judgments on the accuracy of the tuning. In other words, they tune the piano and they play the piano and they go, it sounds good enough. But when we measure the strings, we can see that it's not the ideal equal temperament that we're looking for. And another problem is that most conventional oral piano tuning methods are vague and require multiple passes to get to this point. So it's kind of inefficient. But that's where the Go8 method shines. So here is visually what's going on. We start by measuring a fluctuating string, and then the ETD will approximate the partial frequencies, and then from the partial frequencies, it will approximate the string inharmonicity. And then it will approximate the inharmonicity of all the other strings. And from that, it'll approximate a stretch curve. And then it will backwards approximate the fundamental frequency of each string with the hope of getting progressive beats. For the ear, what we do is we listen to the intervals and set progressive beats. No middle steps along the way producing cumulative error. So this idea of the ETD being more accurate than the ear is one that goes against the Go8 oral piano tuning system, because this system is designed to be accurate, precise, and efficient, and it is. And it helps technicians produce excellent tunings by ear that rival any electronic tuning device.